Okay, so I'm going to do a few more examples of curved Darwin mechanisms, and we'll do a couple, including, I think, some that we actually had on the worksheet, or at least one that we had on the worksheet. So let's look perhaps at, say, the reaction of the iodo alcohol with sodium hydride. So I have the 1, 2, 3, 4, 5. Treat this iodo alcohol. So this would be 1, 2, 3, 4. So it's 4 iodo butane 1-ol. That's sodium hydride. And the product of the reaction is tetrahydrofurane. Okay. So again, we've got to figure out where have our pieces gone, and I'm going to use the oxygen as a marker. And I can see the O is attached to a methylene, well, it's attached to methylene, which is attached to another methylene, to another methylene, to another methylene. So I can imagine then that if I call this carbon, this the alpha carbon, beta carbon, the gamma carbon, delta carbon, well, if I pick a direction, say this would be alpha, this is beta, this is gamma, and this is delta. So obviously what's happened is the oxygen on the alpha carbon has bound to the delta carbon. So I've made, in other words, an oxygen carbon bond. I have broken the oxygen hydrogen bond. I have broken the carbon iodine bond. And of course, sodium hydride contains sodium plus and H minus. Of course, it must, because the compound is neutral. And if the sodium is bound, it can only be bound as Na+. There's no other version of sodium that's reacted. So the H therefore must be H minus. And of course, once the metal is in its cationic form, especially if it's a main group metal, then it really is a spectator ion, and we can, for all intents and purposes, assume that the active species, in fact, is H minus. All right, so what are we going to do? Well, clearly we've broken an OH bond, and that bond is going to be fairly acidic. And we have to decide on what reaction is first. Well, H minus is electron rich, therefore it's going to be a base or a nucleophile. Well, which role does it play? Well, a nucleophile is going to be bound to the product. Right? We've talked about that before, that what a nucleophile does is it reacts with, say, RCl or something, and it does an attack and gives rise to a product in which a nucleophile remains bound to the molecule and there's a leaving group. On the other hand, what a base does is quite different. A base will attack a proton and give rise to BH. Well, in fact, it gives rise to BH and is not incorporated in the product. And this should be a sort of a bad example to draw. Let's have H, let's do it this way. So we'll attack here, we lose chloride, we get BH and chloride, but in the end, the base is not incorporated into the product, okay? So if I redo my example and I say I have this thing attacked by a nucleophile, then the nucleophile will attack the carbon, the chloride would leave, and it'll end up with a product in which the nucleophile is bound to product. So the point is, nucleophiles are bound to product. Bases simply abstract protons and vanish. So I have to ask myself, look, I mean, what's happening in this reaction? And I can say, well, obviously, we have a proton on the O that has gone missing. So obviously, something has taken off the proton or deprotonated the alcohol. And it's not a coincidence that H minus is present in the system. So I can imagine then that the first step in the reaction is the acid-base reaction between hydride, which of course has to be a very strong base because it's H, which is not electronegative. It's also the world's smallest atom that bonds. And so H minus has to be a very intensely charged species. It will be fairly basic. So H minus is going to take off the proton, this H already has a hold in these two electrons. It can't take two more, and therefore it's going to dump the electron pair on the O. And I would have converted a lone pair into a bond pair. And you notice I'm putting the electron pair between H and H because I'm making a bond. And I'm converting a bond pair of electrons into a lone pair of electrons on the O. That's an acid-base reaction, and that's going to give me H2, okay? And I'll generate the iodoalkoxide, which is this species, okay? So, of course, I have charge balance and mass balance. I've lost H2, and the O has picked up the minus charge from the hydride. Well, what happens next is I've converted the O into a much more potent nucleophile, and I know this carbon has a delta plus charge because it's bound to the iodine. So I've got a nucleophile, I've got an electrophile built into the molecule. So this is just a match made in heaven. And I could sort of redraw the species then to look as follows. I have O minus, and I can redraw them to look like so. All right. So here's my alpha, beta, gamma, delta carbon. My O minus can do an attack on the delta carbon. I will lose iodide and give rise to my target product. So the product of the reactions then will be hydrogen, which will be lost in a fairly exothermic reaction, and then iodide, which comes off as a result of the nucleophilic attack of the O minus on the delta carbon. Okay, so let's try another one. Let's try, for example, the reaction between methane thiol and, say, acetone. And that's going to give rise to this compound. Okay, and we want to draw a curved arrow mechanism for that reaction. Well, if I look at methane thiol, I can say, what are my nucleophiles and electrophiles in that molecule? And what are the nucleophiles and electrophiles in the ketone? Well, certainly the H is bound to sulfur, and therefore the H will carry a delta plus charge. And I can make the same argument for the methyl. The sulfur is bound to these two, and sulfur is more electronegative, and therefore the sulfur bears a delta minus charge. So I can say the H is electrophilic or acidic, the methyl is electrophilic, the sulfur is nucleophilic. What about the carbonyl? Well, there's certainly lone pairs of electrons in the O that will confer nucleophilicity to the oxygen. There's a pi pair of electrons here, but I would defer to the lone pair of electrons because lone pairs of electrons are more nucleophilic than pi pairs. So the nucleophile in this system will be the O, and of course the carbonyl carbon will be delta plus. And again, remember now with carbonyls, you have two effects that are operational. One is the inductive effect along the CO bond, the CO sigma bond, because O being more electronegative than carbon will bleed electrons from the carbon, making the O delta negative and the O and the H and the carbon delta positive. But in addition to the inductive effect, there is a companion resonance effect, which confers upon the carbonyl O a minus charge and upon the carbonyl carbon a positive charge. So these actually reinforce the inductive effect. Therefore, the carbonyl carbon is actually a pretty good electrophile. So really then, I have two choices. I can either have the S of the thiol attack the carbon of the ketone, nucleophile for electrophile, and that's reasonable, because of course this S has two lone pairs of electrons on it. Or I can have the O of the ketone attack the H of the thiol. Now, this reaction will be an acid-base reaction, and acid-base reactions in general are the fastest reactions in organic chemistry as long as they're legal reactions. In other words, as long as I don't break some acid-base rule. So, I have my ketone attacking the thiol. That's going to give rise to the protonated species. So I'm going to write the mesylate ion, the thiolate ion, and the corresponding protonated ketone. At that point, what I've done is I've made the OH bond, and it becomes a fairly straightforward idea now that we have the sulfur attack the carbon, and I'm going to break the labile bond in the system, which is the pi bond, and that's going to give rise to my product. It's MES and the carbonyl carbon. I'll have my OH group, and then I'll have my two methyls. Now, let's make a quick point. A common question that people ask is, well, the positive charge on my O is here, positive charge on the molecule is here, and the sulfur is negative. Why don't I just have the sulfur attack the O? And the answer is, if I had let the sulfur attack the O, you have to bear in mind now, with your Lewis structures, there's a low number of electrons in this O, right? Which is why I have 1, 2, 3, 4, 5 valence electrons belong to the O, hence a plus charge. So this O already is an octet, 2, 4, 6, 8. If I have the S, which is negative, and that S has 3 lone pairs, if I have them bond to the oxygen, what I would get almost looks attractive, because I would have quenched the positive charge on the oxygen, but in that action, I would have ended up with an O having 2, 4, 6, 8, 10 valence electrons. So that's impossible. So I can't have the sulfur directly attack the oxygen, because it violates very fundamental precepts about how many electrons can occupy a second row element. Okay, so the octet rule would be violated. But in the end, I don't have to attack the O directly to neutralize it, right? The sulfur with the minus charge attacks the carbon. The carbon then dumps 2 electrons onto the O, and in that process, the O becomes neutral. Okay, so I don't have to do a direct attack. I could very easily do an attack through the carbonyl group. Okay, let's try another one. What about, say, the reaction of cyanide? Oops. The reaction of cyanide with an oxyrane in the presence of, let's say, water, and that's going to give rise to this compound. Okay. Well, let's figure out where things have gone. So obviously Cn is C triple bond N, that's this unit. I have I have 2 methylene groups that are bound to an O. Here's one methylene group, here's another methylene group, and that's bound to an O. So in a sense, then I can say if this is alpha, and they're both alpha, this is alpha prime, I can say that what's happened is I made a bond between the carbonyl, the carbon of the cyanide, and the alpha prime. And so this will be the alpha prime here. The alpha prime is still bound to the alpha is still bound to the O. So what's really happened is I've made an OH bond, I've made a carbon-carbon bond, I have broken a carbon-oxygen bond. And that is in essence what's happened in the reaction. Well, let's see. Let's see, what should we do first. Whoa, that's exciting. Okay. So what should we do for, oh, let's get rid of these as well. Oh, for heaven's sake. So let's see what we should do first. Well, I could argue that in the presence of, in fact, let's make this H3O+. It'll make life a little easier. I'll stop it. Let's make this H3O+. So I can say, well, the proton transfer is the fastest reaction in organic chemistry. And H3O+ is an acid. Acids do one thing and one thing only, they protonate. So I can imagine then that the acid will protonate the oxyrane. This is called an oxyrane. right? And the lone pair of electrons on the O will attack the H. It's an acid-base reaction, so it's in equilibrium. I'm going to lose water, and I'll make a protonated oxyring. It's called an oxyrenonium ion. The cyanide is a pretty good nucleophile. I can imagine that this carbon will be very delta positive because of its attachment to an O+. And so it's not unreasonable then that the cyanide as a nucleophile will attack this carbon, and this carbon already has an octet, right? The H's that I'm not showing here. So it's got 2, 4, 6, 8. It can't accommodate the extra electron pair from the cyanide. So it's going to give up 2 electrons. And the question is, to which atom will the 2 electrons go? And the answer is obviously towards the O, because the O is O positive, therefore it's very electronegative. It's been sucking electrons anyway, so we're just going to give the O what it wants. So the incoming electron pressure from this Cn minus will force these 2 electrons onto the O plus. So this is my source of electron density. This is my sink. And what we'll end up with will be my product, right? I'll have Cn attached to a carbon, attached to a carbon, attached to OH, and that's my product. Okay? Let's do one more. Let's do the reaction between ethanol and HI to give rise to ethyl iodide. Well, ethanol is that molecule, and HI is that molecule. And again, I can do the same thing. I can say, well, you know, the I is delta minus, and the H is delta plus. This is delta plus, this is delta minus, this is delta plus. And I can say, well, you know, the iodine is delta minus, and perhaps I can have the iodine attack the delta plus, right, the ethyl group. And that's possible because I need to make an ethyl I bond. But if I have the HI attack the ethanol via the lone pair of electrons, right, and this makes sense to a certain extent because this is delta minus, that's delta plus, so that can certainly happen. What will have to happen is that I'll have to break the OH bond. And if I did that, my products would be HI ethyl plus and OH minus. And that is illegal on so many fronts because HI is my base. This would be my conjugate base, right? And this is my acid. This would therefore be the conjugate acid. And clearly, HI is a stronger acid than ethanol. Therefore, HI plus is way stronger than ethanol. So I'll be making a much stronger acid from a weaker one, and that's impossible. In a similar fashion, hydroxide is a much stronger base than HI, and so this reaction is completely impossible. So even though the iodine is nucleophilic and the ethyl is electrophilic, I can't do that reaction because it defies acid-base rules. For the exact same argument, I can't look at the alternative, which is to have the iodine of HI attack the delta plus charge on the ethanol. Because if I did that, right, I would be creating ETO minus and HIH plus. Again, very strong acid from a relatively weak acid. Very strong base from a relatively weak base. So that's impossible. The other reason is the O is off of the alkyl group. In the product, the O is gone. So I don't want to do anything that leaves the O on the molecule. So, you know, having exhausted the option of having the I attack the H or the I attack the ethyl, because reactions are disallowed by acid-base rules, my last option is the ethanol has to act as a nucleophile, because it clearly is not acting as the electrophile in the first step. Right? So I'm going to have the ethanol act as a nucleophile, and I'm comfortable with that because should the ethanol act as a nucleophile, right? Should the ethanol act as a nucleophile, what I'll really be doing is an acid-base reaction. I'll have the O act as the base, the HI act as the acid, and acid-base reactions, proton transfers between heteroatoms, are extremely fast and therefore the first. So I'm comfortable with the ethanol acting as a base, attacking HI, right, and giving rise to my product, well, at least for the first step, which is the oxonium ion. Okay, and I'll make I minus. Okay, I'll put the I minus here. All right, so I'm going to generate I minus. Well, I minus is an excellent nucleophile. So since I need to make an ethyl iodine bond, I can have the ethyl be attacked by the iodide, and I will lose water and generate my product, which is ethyl iodide, and I'm going to lose H2O. Right? Now, just notice this is a push, pull, okay? And both of these are equilibria because I have an acid-base reaction, so that's an equilibrium. And I have a reaction which water is essentially leaving a positively charged species, so that's going to be an equilibrium reaction. There's a point I want to make here, which is, you know, I could look at the option of the water simply coming off of the oxonium ion, like so, and giving rise to an ethyl cation, which will look like this. It's CH, well, for heaven's sake. Right? An ethyl cation, which will look like this. And then I can imagine water acting as a nucleophile, attacking this species to give rise to that entity. Oh, lost my train of thought, I'm sorry. Not water, but iodide reacting with this species to give rise to my product. The problem is this is impossible because the ethyl cation is a primary carbocation. And primary carbocations are very unstable. They will not form unless they're somehow resonance stabilized. Okay? So if they're resonance stabilized, then I can form a primary carbocation, but not otherwise. So this is not an option. So this is not a pathway that's allowed. Right? This is impossible. Okay? So the pathway the reaction follows is protonation of the O, then nucleophilic attack by iodide on the oxonium ion. Right? This is called an oxonium ion to give rise to product. Okay. So I'm going to stop there, and hopefully this has been of some assistance. I do owe you guys an extra lecture on the homework on the exam. Okay? Good luck, guys. Bye-bye.